So, in this lecture we shall be starting our discussion on how to design parallel adders. Earlier we had seen how we can design a half adder and a full adder. We shall be using these as the basic building blocks to design the so called parallel adders. So, the title of this lecture is design of adders, the second part. So, we mentioned in the previous lecture also that we shall be looking at various designs of n bit parallel adder. So, what is an n bit parallel adder? It means that I have a circuit where there are two inputs I am applying, let us call them a, b, x, y, whatever you call, let us say one is x and one y. Both of these are n bit numbers, we show it like this. If you cut it and write n, this means these x and y are n bit numbers. This is a shortcut way of showing it. And in the output we generate a sum, this will also be an n bit and a carry. Carry is a single bit. This is what we mean by an n bit parallel adder. We want to design a circuit like this. Okay? Fine. So, the first design that we look at is something called a ripple carry adder, and it very naturally and directly mimics our hand computation, the way we add by hand. We add the bits stage by stage, we accumulate the carry goes to the next stage, the carry gets added with the two input bits at the next stage, again carry is generated, it goes to the next stage and so on. Okay. So, the ripple carry adder essentially just works on this principle. We take n full, that means we want to design an n bit adder. We take n full adders and simply cascade them, connect them one after the other. So, I shall show you how they are connected, and the connection should be such that the carry output from a particular stage, let us say the ith stage, must be applied as the carry input to the next stage. This is how we do addition by hand. So, in the last lecture we took an example that we can have an example where the carry can ripple through all these stages during addition. So, let us show that example once more. So, if we have two numbers like this that you are adding, so initially there is no carry, I am assuming 0. So, I am adding them up, the carry is going here, I am adding these 3 numbers, again carry is going here, I am adding them up. So, the carry is going to the next stage. So, if I call any one of the stage as stage I, so the carry of stage I that is generated will be going as the carry input of stage I plus 1, right. The sum is generated and the carry will be generated. So, you see, if I have a full adder now, if I have a full adder like this, where the two inputs that are coming, let us say the two input bits are applied here, I get the sum, that sum bit is generated, and whatever the carry is generated, the carry, this is my carry out, and this is your carry in, right. And if you use another full adder side by side, this carry out will be connecting as the input carry in to the next stage. So, your inputs are again coming, the next sum you are generating. So, exactly what you are doing by hand you are trying to do like this. See, for the first stage, because the carry is 0, you will be applying a 0 here, right. And for all other stages, the carry in will be coming from the carry out of the previous full adder, and the two inputs will be applied here, and you will be getting the sum bits here, and the carry bits will be generated here, right. So, this is how an n bit full adder looks like. You see, there are n number of stages there are n full adders FA0, FA1 up to FAN minus 1. The two input numbers are A0 to AN minus 1 and B0 to Bn minus 1. C0 is the input carry, sum is generated S0 to Sn1 and a final carry out Cn is also generated. Now, just the point to note is that, well, if this n bit adder you are using in the standalone mode, which means this carry input is always 0, then this first stage of this addition, which is a full adder, you can replace it by a half adder, because half adder, if you recall, has only two inputs. So, this will only have A0 and B0, A0 and B0, and it will be generating S0 and it will be producing C1 as the carry out. Okay. So, if we have an adder design where there is no carry input, then you can replace the last stage by a half adder, which will be a little less expensive because number of gates in half adder is less than that of a full adder. Okay, fine. So, what we have said is this: there are two numbers we are adding, one is A, another is B, both are n bit numbers, input carry is C0, sum is this and output carry is Cn. Now, let us look at the delay calculation. First, look at the carries. You recall, for a full adder we had said the delay for a carry, that means the carry out, delay is twice delta, because there are some AND gates followed by an OR gate. There is two level circuit, delta plus delta. That is why, if you see here, we have seen that suppose A0, B0 and C0 has been applied at time t equal to 0. So, when will C1 be generated, the carry out of this, after a time 2 delta. So, if you look at the time, suppose this is your time. So, this is time t equal to 0. At time t equal to 0, all the inputs have come, all the inputs have been applied, okay? All the inputs and also C0. So, at a time twice delta, C1 will be generated. So, at time twice delta, this new value of C1 will be fed as an input to FA1. So, even though A1 B1 is applied earlier, but the carry input is coming now at 2 delta. So, this will be requiring another 2 delta time to calculate C2. So, C2 will be generated at 4 delta time, C2. Similarly, C3 will be generated at 6 delta time, right. So, in this way, if you continue, then C n minus 1 will be generated after twice n minus 1 delta, and the final carry output 2, 2, 2, 2 like that, it will be generated after twice n delta, right. This is the total delay for the carry. Now, let us see what will be the total delay for the sum. Now, you recall, for a full adder, the delay of a sum is 3 delta, because there is an XOR function, and XOR is not AND and OR. So, it requires thrice delta. So, assuming that again all the inputs are coming at time 0, this sum S0 will be generated after time 3 delta, because it is an XOR of A0, B0 and C0. Now, what about S1? Okay, you remember just now what you said here, that C1 was generated at time twice delta. So, it will take another 3 delta time. Now, A1, B1 and C1 has come at 2 delta, it will take another 3 delta time. So, at 5 delta this S1 will be available. Now, again for the next stage, C2 is generated at 4 delta. So, S2 will be 4 delta plus another 3 delta for this addition. So, 7 delta. So, it goes like this. So, finally, for Sn minus 1, if you just see, expand this, it will be twice n minus 1 delta plus 3 delta, which is 2 n plus 1 delta. So, you see the delay of the carry is 2 n delta, delay of the sum is a little more 2 n delta plus another delta. So, one characteristic of this kind of ripple carry adder is that the total delay is proportional to the number of bits, you see 2 n delta, 2 n plus 1 delta, something like that. So, what it means, if I want to design a very large adder, say 8 bit adder, 16 bit, 32 bits, 64 bits, then my addition time will go up. A 16 bit adder will have double the delay as compared to an 8 bit adder. 32 bit adder will have 4 times delay as compared to an 8 bit adder. So, it is not so easy to expand the number of bits in an addition without sacrificing on the delay. Okay? This is one main drawback here. Now, let us see how we can design a subtractor. Now that you know that how we can design a ripple carry adder. So, for parallel subtraction we rely on our that old number theoretic knowledge, number system we talked about. We talked about the 2's complement number system. We said when you subtract two numbers, it is nothing but you take the 2's complement of the second number and add, that is as good as subtracting. Okay. So, when you say that we are trying to compute a minus b, we can do the same thing by adding the 2's complement of b to a. And what is 2's complement? It is 1's complement plus 1. And what is 1's complement? You are doing not of all the bits. Let us say xi denote the not of bi. Let us look at an arrangement like this. So, what we have shown here is nothing but a ripple carry adder, you see same ripple carry adder, but the only difference is the second input, instead of applying b0, b1, b2, we are applying x0, x1, x2 and xn minus 1. And what are these x's? These are not of the corresponding b values, which means we are adding a with the 1's complement of b, 1's complement of b, right, because 1's complement means just not, but we want to but we have to add 2's complement, right. So, what we do, we also add a 1 to the carry input. So, effectively what is happening? I am adding the 1's complement of b from the top and an additional 1 I am adding as carry input, which means it is becoming 2's complement. So, whatever this sum is coming out, it is actually the same as a minus b. So, I am able to carry out subtraction just by taking the not of the second number and by feeding a 1 in the carry input. It is as simple as that, right. So, subtraction is very easy, we do not need a separate subtractor for that. We can use the same addition hardware, same addition circuit with small adjustments. Okay. Now, let us see whatever we have shown here, how we can make it general. General means a circuit which can do both addition and also subtraction. So, let us see how that circuit will look like. This circuit will look like something like this, where this is our adder. This can be a ripple carry adder, let us say we have seen only one kind of adder so far. This can be any kind of an adder, let us say ripple carry adder. So, what we are doing, the first input A we are applying to this adder. The second input, actually what you are applying, this is the second input B, okay, but we are not applying B directly. There are some XOR gates. So, there are some exclusive OR gates. What we are doing, let us say the ith bit bi, and the second input of this XOR gate we are applying a control input. Let us call it this add subtract, let us in short call it P, let us call it P. So, how does XOR gate behave? I talked about it earlier. It says if P equal to 0, if the output is F, if P equal to 0, the output is nothing but Bi. But if P equal to 1, then the output becomes the not of Bi. Okay. So, it is a controlled inversion. Now, let us see what happens now. Let us suppose this add subtract control input I have applied a 0. 0 means this XOR gates, these B's will pass straight. So, I have A here, I have B here coming directly, and carry input is also 0. So, this is just like addition, normal addition, and in the output we will be getting A plus B. Right. Now, suppose I apply add subtract control input 1. So, if I apply 1, what will happen? First thing is that XOR gates will be doing the NOT of each of the BI's. So, A will be applied here, but here it will be 1's complement of B, 1's complement of B will come here, and carry input is also 1. So, basically 2's complement will get added, and what we will get is A minus B. So, we have a circuit with a control input, which if I set it to 0, it will do addition, if I set it to 1, it will do subtraction. Okay. So, this is a very general kind of a thing, just addition subtraction circuit. Now, let us look at what is the drawback of this ripple carry adder. Drawback of the ripple carry adder is that the total delay we have seen earlier is proportional to n. So, as we increase the number of bits, the delay also increases, there is a degradation in performance. But in reality we need to design adders that are pretty big, 32 bit, 64 bit addition. Not only that, we want to make them very fast, we want to carry out the addition in a faster way. So, how do we do this? Well, one alternative may be that if possible you generate all the carry bits in parallel. Why? Because in a ripple carry adder, the main bottleneck was the carry, which was propagating sequentially from one stage to the next. So, somehow if you can generate all the carry bits in parallel before the actual addition starts, then after that all the additions can be done in parallel, because we have generated all the carries and we need not have to wait any further for the carries to propagate. This is the basic idea behind the next kind of adder that we propose, that we shall discuss, which is much more efficient in terms of the speed, in terms of the delay. This is called a carry look ahead adder. Let us say the basic idea what a carry look ahead adder is. We have mentioned this in the previous slide also, that the propagation delay of a ripple carry adder is proportional to n, but in a carry look ahead adder we are generating the carry signals in parallel. This is a notation which we use to denote complexity, but you need not have to worry about the exact meaning of this. This order n roughly indicates it is proportional to n, and order 1 means it is constant. So, in a ripple carry adder, the total time taken is proportional to n. So, if you make a bigger adder, the time increases, but in a carry look adder what we are saying that the addition time is constant irrespective of the value of n. but the drawback is that hardware complexity, number of gates, size of gates, they will increase very rapidly with the value of n. This actually limits the value of n to a certain value. Beyond that, a carry look ahead adder can become very complex. Let us see how it works. So, we look at the full adder again. Look at the ith stage of the full adder. Just with respect to the ripple carry adder, you just imagine that in the ith stage the inputs were A I, B I and the carry input C I, and the outputs were sum S I and the carry C I plus 1, which was going to the next stage. Now, we define two functions called carry generate and carry propagate. Well, in terms of the inputs A I and B I only. These are my two input bits, okay, which I am trying to add in the ith stage. First, I am calling carry generate. Generate means under what conditions of A I and B I a carry will always be generated. You see, whenever A I is equal to 1 and B I is equal to 1, then irrespective of what my carry input is, this carry out will always be equal to 1. This C I plus 1 will always be equal to 1, because if this is 1 1, if carry input is 0, then also there will be a carry, if carry input is 1, then also there will be a carry. So, I can express this as the AND function, AND of A and B. If it is 1 1, then only it is 1. And the second one is carry propagate. Carry propagate says that suppose there is an input carry, C I is 1. So, under what condition this 1 will propagate to the output? That means, there will also be an output carry. Propagate means under what conditions of A I and B I this 1 will propagate. You see, if it is 1 1, then it is generating carry anyway, but for propagation the two condition will be, one of them will be 1, either 0 1 or 1 0. If it is 1 0 1, then also there will be a carry out. If it is 1 1 0, then also there will be a carry out. So, this is the condition for carry propagation. 0 1 and 1 0 is nothing but the exclusive OR function. Carry out will be 1 if A is 0 B 1 or A 1 B 0. So, your generate is your AND, propagate is XOR. This is what I have just now explained. Now, the output carry C I plus 1 we can now generate or express in terms of P I and G I. How? We can simply write the carry output is either there is a carry generated or the carry propagation condition is true and C I is 1, there is a input carry. So, only under this condition C I plus 1 will be 1, means either a carry is generated, this A I B I both are 1, or P I is 1 means exactly one of them are 1 and C I is also 1, right. Okay. So, we have this relation. Now, if we go on expanding this C I plus 1 equal to this C I can write like this, multiply this out, I get this. The C I minus 1 I can again write like this, I again multiply, go on doing this. So, this you can go on continuing. So, if you go on continuing, so you go from I minus 1, I minus 2, so on, you go up to the last stage. So, the last term, in the last term what will happen? This P I P minus 1 it will go on, P I minus 1, so on, the last one will be P 0 and then you will be having C 0. This will be the last plus something. So, this whatever you are getting, you can check this, you can express this in a concise form like this. C I plus 1 equal to G I will be there, last term will be there, last term is this as I said, C0 multiplied by the product of all the P0s, Pi's. Then the intermediate terms, there will be summation of some Gk and then the products, like you say P1, P2, Pi minus 1, P1, P2 like this. So, it will be something like this. But you really do not need to understand or remember this in that way. So, what we want is that in terms of our design, suppose we are trying to design a 4-bit carry look-ahead adder. So, just using these expressions that we have just now talked about, if we expand them like this, same way. So, I am looking from the reverse way. The last stage C1 can be written as G0 plus C0 P0. C0 is already there, you already know the carry input. C0 is the carry input of the last stage, right. C0 and all the AB inputs are given to you. So, C1 you can generate directly using this equation. Now, C2, if you just apply that previous one, that expansion, C2 will be like this. This you can verify. C3 will be like this and C4 will be like this. And the sums, sum as you know, sum is nothing but the XOR of the 3 inputs in a full adder. Now, A0 XOR B0 is nothing but the carry propagate function. So, propagate XOR the carry is nothing but the sum. So, you can generate the sums like this. So, you see what you need. So, in order to do this, you need 4 AND 2 means 2 input AND 2 refers to 2 input AND gates. You see there is one here, 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 2 input AND gates. 3 input AND gates, one is here, one is here, one is here. 2 4 input AND gates, one is here, one is here, and 1 5 input AND gate, it is here. And similarly, to do this OR operations, you need 1 2 input OR for C1, 1 3 input OR for C2, 1 4 input OR for C3 and 1 5 input OR for C4. And for sum you need 4 XOR, 2 input XORs, right. Now, it is possible to simplify this expression a little bit if you make an observation. The observation is as follows. You see C3 is this, okay. Now, in C4, if you consider this part and if you take P3 common, you see whatever remains G2 plus G1 P2, G0 P1 P2, C0 P0 P1 P2 is nothing but this. So, you can write this as P3 multiplied by C3. So, your expression will become much simpler. You can write it like this straight away, it becomes simpler, and accordingly the size of the gates also becomes smaller. This 5 input AND gate is no longer required at all. So, your cost reduces, right. So, here for this 4-bit carry look-ahead adder, this expression whatever means you have done here generated, if you show the equivalent gate level realization, it is somewhat like this. So, I am assuming that already Pi, Gi are already generated, because Pi, if you recall, Gi is nothing but an AND gate. If you have Ai and Bi, the 2 inputs, this will be Gi, and the propagate function is XOR gate, Ai Bi, this will be Pi. So, I am assuming this P1, P2, P3, all these propagate and generate has already been generated by this. This can be done in parallel, okay. All the stages can generate the Pi and Gi in parallel. This have been generated. Then for the carry generation, I need this circuit. Well, this is after minimization, C3 is being fed here, right. But if you do not do minimization, it will be 2 levels only. So, without minimization, okay, minimization the delay will be little more because 2 again plus 2 4, but without minimization this circuit requires a delay of twice delta and followed by OR, and for pi gi, for gi it is twice delta, for pi XOR it is thrice delta. So, this is more. So, the total delay will be 5 delta, okay, 2 delta to generate these, 3 delta to generate this and 2 delta for this circuit. So, the overall picture looks like this. This is the this is a 4-bit carry look ahead adder scheme. So, you see the 4 bits of the numbers, the 2 numbers A and B are fed to the GI and PI generator. So, as I said, GI is nothing but an AND gate, there will be 4 such AND gates, and PI is nothing but an XOR gate, there will be 4 such XOR gates, and because XOR gate has higher delay, the delay of this stage will be 3 delta. Then after you do this, just in the previous slide the diagram I showed, the 4-bit carry look ahead circuit will be generating the carries in parallel, and because it is a 2-level AND OR circuit, the delay is only 2 delta. Now, for generating this sum we do not need any full adder anymore, because as we saw from the expression, these S's are nothing but this propagate function XOR the carries. So, if you take P0 XOR C0, P1 XOR C1, P2 XOR C2 like this, you can directly generate this sum, and for XOR you need another 3 delta. So, you see the total delay is 8 delta, which is independent of the number of bits, right. But the only point to note is that this you can see from the expressions that you have generated earlier. Just let us go back. These expressions. So, as you go on increasing the number of bits, the complexity of the expression will also go on increasing. The size of the gates, number of gates will increase very rapidly. This is the main drawback. So, total time as I said will be 8 delta. So, with this we come to the end of this lecture, where we have talked about 2 different kinds of parallel adders, ripple carry adder and also carry look ahead adder. So, we shall be continuing with our discussion in the next lecture. Thank you.